Today, I'm going to walk you through Module 8, Chemical Equilibria. In this lecture, we will review chemical equilibria, understand the role of the equilibrium constant, calculate the constant based on formulas that we will go over, and work through a case study to test your understanding using a real-world application. If you remember from the first slide, the molecule that was there is hemoglobin, which will become an important part of our case study at the end of this lecture. Let's start off with some review to jog your memory and brush up on a few important topics. A chemical equilibrium is reached when the rate of the forwards and backwards reaction is equal. There are two main factors that influence equilibrium. The first is the concentration of the reactants, which determines how often reactants will collide with each other. If a reactant or reactants are low in concentration, there won't be very many collisions. But if they're in high concentration, there will be lots of collisions. The second factor that influences equilibrium is temperature, wherein increasing the temperature of the reaction leads to more high energy collisions. All right, let's move on to the equilibrium constant. As we know, this is the formula for the equilibrium constant, when this is our chemical equilibrium that we're working with. The uppercase letters represent the products and the reactants in the reaction. The lowercase letters in the exponent position represent the equation coefficients. The lowercase a, right here, represents the relative activity of the products and reactants, which is a unitless measure most useful when calculating K when reactions involve more than one phase or state. To find the relative activity of the products or reactants measured in concentration, we can use this formula or this relationship up here. And if gases are present and measured in pressure, then this relationship can be used. The standard concentration and standard pressure values are listed right here in the relative activities box. And it is important to note that the relative activity of solids, pure liquids, and solvents are all equal to 1. All right, now that we understand how to format our equilibrium constant formula, let's do a couple of quick practice questions. For this first equation, we can see that the reactants are nitrogen monoxide and oxygen, and the product is nitrogen dioxide. Keeping in mind the stoichiometric coefficients, we can see that this is the formula for K, with our products in the numerator and our reactants in the denominator. With the next equation that I put on the screen, I would invite you to pause the video, try to determine the formula for K on your own, then come back and we'll go through it together. Did you get it right? I hope so. Let's see what the answer is. We have our products in the numerator and our reactants in the denominator, and we have an exponent 2 on both of the silvers because they both have a stoichiometric coefficient of 2. Now that we understand more about the equilibrium constant, one question to ponder is that if we change reactant concentration by an increase or decrease, does that change the equilibrium constant itself? Take a second and think about it. Does it? I want to bring up Le Chatelier's principle, which states that if a change is made to a chemical system in equilibrium, the equilibrium will shift to counteract the change. If the concentration of a reactant changes, the concentration of the products will also change. The equilibrium constant will remain the same even if you calculate K with the original equilibrium concentrations or the new ones. All right, let's move on to our case study. Hemoglobin is a component in your blood that carries oxygen to your organs and tissues and transports carbon dioxide back to your lungs to be exchanged for more oxygen. As such, it is important that your hemoglobin levels are kept at a safe range, and a hemoglobin test can be done to determine whether your levels are where they need to be. If your hemoglobin is below the acceptable range, you would be considered anemic and have a low red blood cell count. However, if your levels are above the acceptable range, then you could be diagnosed with a blood disorder, which is rare. Or other factors could be contributing to this result, including living at high altitude, smoke frequently, or you could just be dehydrated. For the purposes of this case study, you are a doctor in a hospital, and you are presented with a patient in the emergency room. A 65-year-old male patient presents with frequent headaches, dizziness, frequent nosebleeds, and fatigue. You think you may have a diagnosis based on his hemoglobin levels, but you want to know more about his family history. You learn that his paternal grandmother and his maternal grandfather were both diagnosed with polycythemia vera, which is a rare blood disorder. You think back to your knowledge from Chem112 from Queen's University, and you know you can help him. You know that the equation for the chemical equilibrium for hemoglobin and oxygen is right here on the screen. The normal levels of hemoglobin are 0.05 molar. His normal levels of oxygen are 0.07 molar, and normal levels of hemoglobin dioxide are 0.06 molar. However, your patient's hemoglobin level is 0.07 molar, and 0.06 molar for oxygen. You need to find the concentration of hemoglobin dioxide in your patient to determine his diagnosis on whether his hemoglobin levels are where they need to be, above where they need to be, or below where they need to be. Your first step is to determine the K value for this equation using the values given, because as we have covered, even if the concentration of the reactants in an equation change, the K value will not change. So when we lay out our equation for K with our products in the numerator and our reactants in the denominator, we find that 17.14 is the characteristic K value of this equation. This is the equilibrium constant for this reaction that we're going to use. So now we can lay out an ice table. And I invite you to now set up the K formula for this equation using the values from our ice table. We can see that when we lay out our equation, we input our values, we input the value of our K, and then we solve so that everything is equal to 0. Now, this equation doesn't lead us straight to the X value. We need to use the quadratic formula to find the value of X. I invite you to pause the video, solve for X, and come back when you're finished. All right. Now we find that our two X values are equal to 0.16 and 0.0258. Now we have to ask ourselves, both of these are positive, so which one should we use? Well, 0.16 is larger than both of our initial concentrations of hemoglobin and oxygen. So we know that 0.0258 must be our value for X. All right, now that we have the value of X, let's put that back into our ice table and solve for the equilibrium concentrations. Wonderful. So now that we have our equilibrium concentrations, we can compare our hemoglobin dioxide level with the normal hemoglobin dioxide level. What does this mean? Pause the video and determine your diagnosis for this patient. Because this 0.0258 is below the normal level for hemoglobin, you determine that your patient has anemia.